What specific problem does your proposed method aim to solve in the context of software engineering tasks on SWE-bench, and how does it differ from existing approaches?
Our proposed method aims to address the inefficiencies of existing agentic frameworks in software engineering tasks on SWE-bench by simplifying the agent design process. Traditional approaches rely on complex scaffolding and interactive exploration to gather information, which can be cumbersome and tailored to specific models. In contrast, our method leverages long context language models, LCLMs, to directly process the entire state of the code repository, effectively transforming open-ended tasks into closed-ended ones that LCLMs excel at. This scaffolding-free approach not only reduces the need for specialized tools, but also enhances performance, as demonstrated by our DIRECTSOLVE method, which outperforms existing baselines by 3 to 6% without additional scaffolding. Furthermore, we introduce a two-stage SWE-bench method that combines LCLMs with short context models to optimize performance, showcasing a significant improvement over traditional methods while maintaining simplicity in design.
How does the proposed method work? Please illustrate it step by step, detailing the roles of DIRECTSOLVE and SWE-bench.
The proposed method operates through two main approaches, DIRECTSOLVE and SWE-bench, both leveraging long context language models, LCLMs, for software engineering tasks. 1. Direct solve. This method directly prompts an LCLM with the entire or compressed code repository and the problem statement, allowing the model to generate a solution in a single inference call. It employs two effective prompting techniques: code restatement, which helps the model retrieve relevant code snippets, and chain of thought prompting, which breaks down the problem-solving process into smaller reasoning steps. This approach eliminates the need for complex scaffolding, enabling the LCLM to perform tasks like localization and bug fixing efficiently. 2. Select solve. This method combines the strengths of both LCLMs and short context language models, SCLMs. In the first stage, an LCLM identifies and compresses the relevant files from the repository based on the problem statement. In the second stage, the compressed information is passed to an SCLM, which specializes in generating code repairs using the localized files. This two-stage approach optimizes performance by leveraging the LCLM's long context capabilities for localization and the SCLM's superior problem-solving abilities for code repair. Overall, the method simplifies agent design by minimizing the need for manual pipeline curation while maximizing the utility of LCLMs in software engineering tasks.
Can you provide a specific example of how the DIRECTSOLVE method prompts an LCLM to generate a solution based on the entire, or compressed, repository state?
The DIRECTSOLVE method prompts an LCLM by directly providing it with the entire, or compressed, repository state, along with the problem statement. For instance, when the code repository fits within the context length limit, the method prompts the LCLM to generate a solution by inputting the problem statement alongside the complete repository state. This is illustrated in the paper where it mentions that the LCLM is prompted to generate the solution based on the problem statement and the entire, compressed repository state, effectively allowing the model to reason and solve problems in a single inference call. Additionally, the method employs prompting techniques such as code restatement, which acts as an in-context retrieval mechanism, and chain of thought prompting, which breaks down the solving process into smaller reasoning steps. These techniques enhance the LCLM's ability to extract relevant information and produce accurate solutions without the need for additional scaffolding.
What are the theoretical or practical benefits of using the long context LMs, LCLMs, in your method over traditional agentic frameworks?
The theoretical benefits of using long context LMs, LCLMs, in our method include the ability to process the entire environment state directly, which eliminates the need for complex scaffolding and iterative exploration typical in traditional agentic frameworks. This simplification transforms open-ended tasks into closed-ended ones, allowing LCLMs to leverage their long context processing capabilities effectively. Practically, our approach demonstrated a performance improvement of 3 to 6% over existing scaffolding-based methods, showcasing that LCLMs can outperform complex pipelines without requiring specialized tools or extensive manual curation. Additionally, the use of LCLMs reduces the compounding errors associated with multi-stage pipelines, as they can directly extract relevant information and produce solutions in a single inference call. Overall, LCLMs not only streamline the agent design process but also enhance localization accuracy and problem-solving efficiency in software engineering tasks.
How was your method validated? Describe the experimental design, datasets used, and the performance metrics you applied to demonstrate the effectiveness of the method.
Our method was validated through a series of experiments using the SWE-bench verified benchmark, which consists of 500 carefully selected software engineering problems with correctness verified via unit tests. We implemented two primary approaches: DIRECTSOLVE, which directly prompts a long context language model, LCLM, to generate solutions based on the entire or compressed repository state, and SELECTSOLVE, which combines LCLM for localization with a short context language model, SCLM, for problem solving. Performance metrics included the pass-at-1 rate, measuring the solve rate of the final selected patch, and the pass-at-8 rate, indicating the rate of at least one successful patch among 8 samples. Our results showed that DIRECTSOLVE outperformed the best baseline, agentless, by 6% on pass-at-1, while SELECTSOLVE achieved a significant improvement from 39.2% to 48.6% when using CLA-UDE3.7 Sonnet, demonstrating the effectiveness of our scaffolding-free approach. Additionally, we conducted an ablation study to analyze the impact of various design choices, further validating the robustness of our method.
What limitations or drawbacks have you identified in your proposed approach compared to state-of-the-art agentic systems, particularly in terms of capabilities and performance?
Our proposed approach, while demonstrating competitive performance, has notable limitations compared to state-of-the-art agentic systems. Primarily, the long-context LMs, LCLMs, used in our methods exhibit relatively weaker coding capabilities than specialized short-context LMs, SCLMs, which results in a performance gap. For instance, our DIRECTSOLVE method, despite outperforming agent scaffolding by 6% on pass-at-1, still falls short of the best-performing agentic systems, indicating that LCLMs may not fully leverage the intricate problem-solving abilities that SCLMs possess. Additionally, while our SELECTSOLVE method improves performance by combining LCLMs and SCLMs, it still does not match the effectiveness of more complex engineered systems like OpenHand's Codact, suggesting that specialized tool design can yield additional gains. Lastly, the reliance on LCLMs for full-state processing may lead to challenges in handling larger repositories, as evidenced by the need for state compression when context lengths are exceeded, which could hinder performance in more complex scenarios.